In the last video, I was showing you the idea behind this. But an idea isn't real until you draw it on a whiteboard. This first picture shows the image. Now remember, I made this before I had any software. It just shows you looking down into a tunnel, and it goes off to infinity. Next, I drew a cross section. This is where it got serious. This is where perspective comes into play, and it's hard to have any real 3D without perspective. This is just a flat piece that goes inside. Remember, the walls of the tunnel are two-dimensional. You can say how far down the tunnel you are, or what position around the tunnel. The around part is easier to deal with, and you'll see that in the code. It's just one line of code. The down the tunnel part is where we needed to add the perspective. This third picture is just a subset of the second picture. I just pulled out a single triangle. This one triangle is labeled with X and Y, so you can make it anywhere you want, in any size you want. X says where we are on the computer monitor. Y says where we are in the tunnel. Once you have a triangle, then the math gets really easy. Most important thing here is similar triangles. So I'm comparing the smaller triangle to the larger triangle. They both have the same angles, so the lines are going to be proportional. X divided by Y is the same as radius divided by this longer line, which is Y plus offset. Offset's the part that I didn't even think about right away. This red line here, that's the computer screen. And this point where everything came together, that's the eyeball. So the picture only makes sense when you know where the screen is and where the eyeball is. The idea is that looking at the computer should be identical to looking into the tunnel. For every point on the computer screen, there's a corresponding point in the tunnel. I do some math to do that translation. Then I ask, what's at that exact spot in the tunnel? What color is it? And I draw that color on the screen at the corresponding point. Finally, I did some algebra. X is my input. I chose a spot on the screen to draw, and X says where it is. Y is the corresponding point in the tunnel. That's what I want to know. So I solve for Y. That's the tricky part. Now let's look at some code. The code starts with a lot of variables. Let's discuss these when they're first used. And we have the init once function. You've seen that before. It does exactly what it says. It gets called when we first start, and never again. We've seen the canvas and the context before. That's in several of our lessons. I discussed this briefly in the in Queens problem. We have code behind these buttons. When I click on something, it knows how to change things. And why would I want to duplicate that code here? I don't remember necessarily which variable to set or which one of these is the default when the page first starts. So all I say is just pretend like somebody clicked on whichever buttons were already clicked. Init canvas, that's down below. This is stuff that happens at the beginning, but also anytime we make a major change, like resizing the screen. And then do one step. Well, you've seen that before. It does some work, and then it queues itself up, so it'll do some more work again soon. And we'll definitely take a closer look, but that's the main part that just keeps going and going and redrawing stuff. All right, init canvas, we're figuring out where the center of the circle is. That's infinity, of course. The radius, a few notes here, but basically we made it so it almost fits in the canvas. Then the offset. The offset was how far the person's eyeball was from the computer screen. We could make that changeable. That might be an interesting thing. For now, I just arbitrarily said it's the same as this radius. Context fill style. So this shade of gray, we paint that here and anywhere that isn't part of the tunnel. We just do that all at once. It seemed like it was a little bit faster than doing it one pixel at a time. And just fill everything. All right, we've copied the length formula from somewhere else. That's just the distance between the 2 points, just the Pythagorean theorem. All right, translate to real world. So this is what we've been discussing the whole time. This was all the math we did up on the whiteboard. Taking a point here, so if x is maybe 50 and y is 100, figuring out where that is on the cylinder. We call the cylinder the real world. It's the world we're trying to simulate. We start by saying how far is it from the center? Well, that's what this length 4 is. It's just the distance between 2 points. And then this drawable part, that was this gray stuff. If it's outside of the circle, it just doesn't mean anything to us. And we're just going to leave that gray that was drawn at the beginning. So next we figure out the angle. I promised you the angle would be very simple. It's just this arctangent function. And it's made for exactly that. You say 10 units over and 20 units up, what angle am I from here? That's just a well-known problem. From edge, so we saw these things in the on the whiteboard. Okay, distance. So this is the formula that we've been building up this whole time. And this just comes exactly from the whiteboard. And then finally, the distance, we add this thing called start distance. Start distance is just the place as we are moving up and down the cylinder, and that's how this thing seems to move. So the start distance just keeps moving inward, but it makes it appear like the cylinder is moving toward us. Should have mentioned that these were actually initialized at the beginning. Start distance is initially 0. It's a pretty arbitrary thing. All that matters is the changes to it. Then the start time is the current time in milliseconds. We're precise to the millisecond. That's going to be useful when we update it to make sure we're moving smoothly and continuously. We need to know the time. And we just pack all that up into a single object that has a bunch of fields, like theta and from edge. All right, checkerboard color. Now I called it basket over here. And I don't know why I was thinking basket weave. It's actually a tablecloth is what I was thinking of. But we'll call it basket in here. So this was just what I thought of as the simplest test pattern that I could come up with. I don't know, it's a little bit interesting. It certainly worked well as a test pattern. In fact, let me show you the first time that this failed. So here, see these side by side, you can see that it understood the theta part, the angle, and it broke it up. Now this had a different number of things, but it was doing what it was told. So again, it knew the angle, and that looks right. It has the darker sections and the lighter sections. Problem is this length dimension, it was way off, and you notice how this entire thing looks a lot like the center, and the center is a problem because we just don't have enough detail. It's too far away and we can't quite see it. So the problem is the first time I drew this, I had my formula wrong, and I was squishing everything in that length dimension, and it just looked like this this funny pattern, which is interesting, but not what I was going for. So let's take a look at that code, and actually there's several versions of it. There's only one thing of code, but there's just different inputs to say what colors to use. So this takes in the real world dimensions as an input. So it doesn't even think about this whole translation or perspective or any of that. And then it knows 3 different colors. You have the even and the odd that are shown here, and then you have the diagonals, which were in the basket weave. So the idea was that gray was the diagonal color that's used half the time, and then black and white were used the other 2/4 of the time. Then the period again is 8, it was 4 in that picture I showed you. It's real easy to change stuff. That's why we write it this way. I could have just put 8 right down here, but it's a lot more obvious when I write it like this. And then the question is, how far do I have to go around to get to the next square? Well, this is all in radians. The circle is 2 pi radians around. And you work out the math. It becomes pi divided by the period. So that's how many units you have to go around. Remember the theta that's going to come in here from the real world? That's what we're looking at. And we're saying the first this many units are black, and then the next that many units are white. And now we try to do the same thing going forward, again on this length dimension. And this is, again, the calculation that I had way off before. But basically the idea is this should be approximately a square near the edge. And that's all that I was going for here. It was just a very similar number. And of course, as you go in, everything gets distorted more and more. These look more and more like rectangles instead of squares. All right, distance. We're asking first, how far ahead is this point? And then we're dividing it because we don't want it in these arbitrary units that they came in. We want to divide it because we're just saying we want this square to be a certain size. That's all we're doing is scaling it. Then math floor, that just takes the integer part. So this answer might be, if we just looked at this first part, it might say we're 10.5 squares forward. But we really just want to say 10. We don't care if we're at the very edge of the square or in the middle of the square or anywhere else. So that's all we care about is which square. And then the same thing with theta. We don't care exactly where we are around. We just care if we went enough units to go 1, 2, 3, 4 squares. And again, the same thing. We're going to throw out the fractional part. We don't care if we're halfway through a square. We just want to know which square we're in. And then we check both of those. We've done even and odds before. I think that was in the n-queens problem. And then it's exactly what I said before. If they're both odd, we return the odd thing. So that's 1 and 4 squares. And if they're both even, so exclamation point means not odd is even. So then we use this other color, and that's another quarter of the cases, and then the final half is this diagonal. What about the swirl? Well, the swirl never worked out quite like I wanted, but it's really kind of a hodgepodge of different things. And the best thing that came out of it, even though I'm not really that impressed with this swirl, this is what gave me the idea for the rotated checkerboard that really did work really well. So you can kind of see the direction we went from the normal checkerboard to the swirl to the rotated checkerboard. And the formula for this, pretty simple. Yeah, we have a list of colors. I tried a whole bunch of different colors. That's why there's some stuff commented out here. And this first thing, the swirl palette just selects which set of colors you're using, which foreground and background. So the idea is this only looks at the distance down, and then it picks colors. It doesn't really care about the side to side. And I never had this problem in any of the other code, but for that one point that's off at infinity, it really was infinity, and the code crashed. So I now purposely check, I explicitly check if this is finite or not. And this is the same basic code. It's not quite documented as well. I quickly copied this from some other places. I just cobbled it together, and again, it's a nice idea, but maybe if I had more pixels, I could make this work. And the same thing, we've done this before. We just do the round robin. We look at the first pair, and then the second pair, and then the third pair, and the fourth row that we're looking at, we go back to the first one again. And then somewhat arbitrarily, I say that point in the center is just the first one. It doesn't really matter. I mean, this point in the center, it could be anything. That's the whole point. It's just changing so fast. We just don't have enough details to we just can't fill in those details. Then we just look it up in the array. Again, we're putting a lot of extra details into this, as much as anything, so in the debugger I can ask, what index was it? What was the result? I can just look at that more easily. All right, so swirl color. This is similar to the checkerboard color we just looked at. Checkerboard color. It does the same thing, but for the swirls. Take in a real world point, so a distance and an angle, and it's already has the perspective taken care of, so we don't have to think about that. Period, the square. So we start off very similar to before, but now what we're looking for is that you add these two together. So that's how we get this, this swirl pattern. We basically say, as we're moving in, we have to move around to stay in the same swirl. In and around, and then all we do, it's even or odd again. You should recognize this by now. This is divide by 2 and give me the remainder. And we already selected the colors. Well, someone gave us 2 colors, presumably from this previous function, though it could be anything. And then finally, the rotated checkerboard. Again, very similar to what we've done before, at least we start the same way. So we have the grid lines. That's what we compute with this whole thing, this square around and square forward. This is just transforming that cylinder into a grid. For the checkerboards, filling these in, it was again just the even and odd thing. So let's say flood fill, black, black, white, white. So that's the formula we were using. For this one, we're using the same grid. Yeah, you can't quite tell. But we're using it in a different way. Each one of these cells will have a red, green, blue, or black diamond in it. So let's build that real quick. And flood fill. And I didn't do a great job there, but you get the basic idea. We fill in a diamond of whatever color it's supposed to be. In fact, let's do a second one real quick, I hope. And flood fill. And then the next one, I guess, is a dark blue. And flood fill. And you can kind of see it. We built these diamonds of specific colors, but then the empty space in here is the other color, the white color. So let me flood fill with white. So that's the basic idea. Find which square you're in, pick a color, decide if you're inside or outside. Again, starting with this exact same code for figuring out the squares, but we did make a change. We say that we don't care. Remember, when we're doing the checkerboard, the normal checkerboard, we said we only care about which cell we're in. 1, 2, 3, 4. We didn't care if we were halfway through. Now what we're figuring out is exactly the opposite. We start with the units forward, but then we say throw away the part that was an integer. Just tell me where I am in this cell. Tell me if I'm in the bottom left corner, or the center, or the center right. So again, we only care about the fractional part, the part within this cell. Same thing here with theta. But then we do one more thing. Drawing a diamond was a little bit tricky. Well, you see that this thing is symmetric. So what if I don't worry about the top half? Here, let's draw a rectangle just to hide some of this stuff. So what I said was, if it's in this top half, just flip it over and look at the bottom half. And that applies to all of these. Then I did the same thing in the other dimension. I said this thing is symmetric. It's a mirror image. So let's just block some of this out. Now all I really need to draw is this triangle. Very simple formula. If it's below the line, it's one color. If it's above the line, it's a different color. And there we are. These names, even and odd, are stolen from an older piece of code. It doesn't really make sense anymore. That was for the original checkerboards. But one of these, again, was just a single color. There's the white everywhere. The other one is a list of colors where we have the red and the blue and the green and the black. All right, update distance. So we've been using this distance all over. We've been saying everything is relative to some point, and we just keep sliding that point over time. Now, originally, every time we drew a point, we looked up the current time, but that caused some problems. Here, let's see if I can show you. I don't know if you noticed, each of these has a few more. Each of these has a few more buttons than the last. This only had the 2, and this one had 4, and you just get more and more controls as time goes on. So here you notice how things aren't quite centered. That's a fair statement. So it drew the left side, and then the next column over, and the next column, and over time, finally got to the right side. A lot of time had passed. Now these lines in this dimension are perfect because it doesn't matter. Time doesn't matter to that. Time only matters to these circles to say what the radius is. And that's why things didn't quite line up, because time wasn't right. But we fixed it. We now just, in fact, it's right at the top of this do one step we call update distance. And that updates this number. Get the current time. Again, it's very important. Sometimes the computer is going to be busier than others, and sometimes it's going to call us back right away, and sometimes it's going to make us wait. So we always use the clock. We don't just say always update 5 pixels each time. We say 5 pixels times however much time has passed. We have a second version of this tunnel thing that's even worse. So this one I ended up going back to the tablecloth pattern, and that just made it even more clear that one dimension was perfect, but this other dimension, these circles, it's even further off, and you can see why. I added the speed thing and I made it go faster. So it took just as much real time to make it from left to right, but this faster switch said that since we're traveling faster, more distance was covered in that time. So anyway, that's what bugs look like. They've already been stomped out. Now you can see everything's centered exactly like it should be. And then we just iterate, like I said, we go left to right and up and down. We just look at every single pixel. We've seen all these procedures before. Translate to real world. And it might say that it can't. Those are these edges here that are outside of our field of view. Otherwise, this is where it gets tricky. There's this get color that we only briefly saw. It wasn't a function, it was a variable. Get color. So we'll see in a minute where that variable is set, but a variable can contain a function. So the whole idea is that get color is either going to be red basket or black basket or color swirl. And they all take the same input, this real world coordinate. And then we just draw a rectangle that's 1 pixel by 1 pixel, and that's located exactly at the x and y coordinates that we care about. Oh yeah, you've seen this in the earlier parts when we were debugging. This said how long what the frame rate was, and then the distance, how far we had moved. And then set timeout, you've seen something similar. The only difference is we're waiting exactly 1 millisecond before we try again. That doesn't do a whole lot. That's just being polite. That's just telling the operating system, hey, if someone else is trying to run and they're waiting on me, go ahead. This is a good time, but as soon as reasonably possible, let me draw my next frame. Then update size. That's this button right here. not a whole lot to it. We're saying canvas height equals canvas width. This is the actual number of pixels. This is the size of the bitmap. And again, this gets stretched a lot right now. There's pretty big pixels you can see. And we're just reading both of those out of this text box here. Then we have the display size. So remember, we can, without changing the quality, we can just make it bigger or smaller. And then the display size, this is CSS. That's why it says PX here. And again, we're just reading in the value from the GUI and then shoving it right back in. We're shoving it into that width property. And again, this is just canvas width. This is canvas style width. If you look it up, trust me, this is the what's visible on the screen, how wide it really is. And this is the level of detail, how many pixels. On load init once, we've seen that enough times. The speed selector, we've seen similar things. How many milliseconds per pixel? And finally, we get to this interesting part that we haven't seen before. So when I click on red basket, what does it do? Remember get color? We just saw it a second ago. We called it like a function, even though it's a variable. So what does that mean? Well, we're going to create a new function. Its input is going to be real world. Just one input, and sure enough, that's how we call it up here. Get color, real world. And what's it going to do? It's going to call this checkerboard thing that we've looked at in great detail, only I'm filling it in with certain specific values, not just the real world value that was just given to me, but also these others. These are, well, this is red basket, so it's shades of red, white, and pink. And if you hit red checkerboard, it's almost identical. It sets that get color variable to a new function it created. It's still using checkerboard color to do the heavy lifting, but the difference is that two of these are the same. So that and that are both red. Exactly the same thing for black and almost identical for color swirl. Again, we're not using specific colors, we're using that swirl palette function. And then finally, rotated checkerboard. You can see the colors are black, then red, and then green, and then blue, and then the alternate color is white. So that was kind of clever. I didn't realize that I could, well, I knew I could do that, I just didn't think to do it. And making a function right here and shoving it into a variable definitely made the code very clean. Well, that's about it. I hope you enjoyed this. Check out the link below if you want to run the code yourself or take a closer look at it.